Hello, everybody. Today we continue with our lectures from analog and mixed signal processing. Before I continue, I will explain you what this means. AMOS. AM is analog and mixed. And what is S? S is signal processing. But S is signal for sure. But what is O? O is obrada. Obrada means processing. So in Croatian, it's Amos. So this is just short explanation. Okay, today we continue with one very important topic in our analog and mixed signal processing. It's sensitivity. So we will say a few words about sensitivity analysis of active RC filters. Before we continue, I just want to say that people first invented the RLC ladder filters, which are made of passive components. And those filters that are made of passive components, they have very low sensitivity. So the sensitivity was not topic for research. But the people wanted to replace inductor, and as soon as they have replaced inductor, they have active RC filters. And then all of the sudden, active RC filters started to be very sensitive. So the sensitivity started to emerge as a topic of research. So this is why we are going to tell something about sensitivity theory and sensitivity of active filters, because active filters are today in use very often, so it's good to know something about sensitivity. What is sensitivity? Before all, we can define a linear system with relation from input to output. And this relation from input to output is given by some equation. So this is the equation. And some elements inside this box could be resistors, capacitors, gains, amplifiers, or whatever. So these x1, x2, and 2xn are some values of something that is inside the box. So the question is, what will happen if one of these parameters, you have many of them, what will happen if one of these parameters will change? What will happen in the relation from input to output? And then some people started to think about this, that it will be the most efficient to express the relative change of a function to relative change of any of the parameters. So what does it mean, relative change? If you have a resistor of 1 kilo ohm, and for example, R1 is 1 kilo ohm, and we say this resistor has 1% tolerance. So 1% tolerance, that means the resistor can be, what is 1% of 1 kilo ohm? It's 10 ohm. So R1 can be from, let's say, 9.090 kilo ohm to 1.01 kilo ohm. So R1 can take these values. So what will happen if we have 10 kilo ohms? If we have 10 kilo ohms, we have again 1% tolerance. So for us, it's better to look what will happen if R1 changes in percent. So this is obviously delta R1 over R1. So this is definition of the, let's say, percentage change. So this is one reason why we look at the relative change. There are also many other reasons that are that will be obvious, but before we look at some examples, we will. So this can be multiplied by 100, and then we have percent. We can say from mathematics that every function which has value for the value of one parameter x0. So here we look at Taylor series of one parameter. So if we change one parameter x0 by some amount of delta x, so x0 is absolute value, delta x is also absolute this time. So if we write a Taylor series, then we can calculate the function. What will happen with the function if x0 is changed by delta x? So this is simple. And as we all know Taylor series, and if we say that this delta x is very small, not only small but very small, then we can say that this delta x square can be neglected. So something what is very small, and when it's to the square, to the power of 2, then it's so small that it really can be neglected. So we can say that if we have very small variation, this is important. This is very important to remember, because the whole sensitivity which we are learning is based on the small variation of delta x. Because of this, so if we just look at the first delta x, the first power, then we can write delta f is f of x0 minus plus delta x minus f of s0. So this is nothing else by definition than this first part, and then we can write it in the following form. So delta f over f is delta, let's say like this. This is df over f over dx over x times delta x over x. So this here, this is, let's say, a little bit larger than very small. But here, this part, this is definition of sensitivity. We can write sf to the x. So f can be any parameter, x can be any parameter. So here delta x over x can be a little bit larger, and then we can have approximately delta f over f, which is larger. But what we have to notice here is our definition. So this is our definition of the relative sensitivity. We can write it here as df over f. So this is definition equation. Or we can write it like this: df over dx times x cross over f. So this is also valid notation. So this all is called relative sensitivity. Why relative? Because of this form or the percentage. Okay, now we can continue to see what will happen. Just a moment. What will happen when we use this notation? For example, you know that derivation of, let's say, ln x is nothing else but dx over x. So we can use this also, and sometimes it will be useful. Of course, this is also d ln f is df over f. So sometimes it will be also useful to have this form of the sensitivity, which is nothing else by d ln f over d ln x. So this is altogether not so big deal for now. Also, we can say that those guys here, they can also be measured. And this guy here can be calculated. So we will see it on some examples. So this is the definition of sensitivity. Now we go one step more. You know from mathematics that if function has multiple variables, then it can be represented by, for example, if you have a derivation of something like f of let's say x1, x2, then what is the differential of this f? Let me write like this. This is df over dx1, let's say d, plus df over dx2, So this is something which we all know from mathematics about derivation of function f, which has multiple variables like this. If you apply the same rule here for the function of multiple variables, then you will, and you apply this definition, then you will be able to write this. So to obtain relative change of the function, which has multiple variables, then you must take into account all the variables, because it goes from this rule. So we can call this quantity here, to simplify our things, we can call this variation. So this will be variation of f with respect to xi. This is sensitivity of f to xy, and xy variation by itself. So now we can say that the variation, or delta f over f, is the summation of variation of all variations of f with respect to all xi. So this is something what is logical. Okay. Next, here on this table we have definition of all sensitivities which we know. So relative sensitivity is given here. This is our. But sometimes it depends what we take as f. If we take f that has some zero, and that means dividing by zero will not give us good results. So then we have semi-relative. Then we have only df over dx over x is like in percentage is relative, and df is absolute value. So then we have this semi-relative sensitivity. Those two, relative and semi-relative sensitivities, they are used in most cases. There is also possibility to have another semi-relative sensitivity where is only delta f over f like relative value and dx like absolute value. So, and finally, what is absolute sensitivity? This is the first derivation, nothing else. So this is not big, something very important. This is absolute sensitivity or gradient or the first derivative. And here, of course, we repeat the definition of the term variation. Okay, how we apply sensitivities to calculation of sensitivities to some expressions. We will calculate it now very quickly, but here I just want to tell that there exist relations that are very useful. For example, if f is of the form y of x, plus c. C is constant, it doesn't have x, but this part here, this has x. So what is then the derivation? Let's say like this. What is derivation of f to x? Then it is dy over dx plus dc over dx, and this is 0. So this doesn't. If you make derivation of constant, it doesn't exist. So you just have this part here. So this is written here, and then you go to the definition equation. Sf over x is df over dx times x over f, and this is f has this kind of representation. Then you have dy over dx here, and this is multiplied by x over epsilon of x plus c, and then we can also divide it by y and multiply by y, because y is function of x. What you will have, this is y of x plus c multiplication of what is left. This is y. It is left s y of x to the x. What is s y of x to the x? This is dy of x to the x times x over y of x, which is this what is left here. Okay, so you can check. So this is very simple derivation of the rule. For example, this is rule number 12, and this is extra rule which I want to show you because it's very important. There are also another very important rule. For example, if there is multiplication of two variables, then you can make derivation, which is like this. You know this rule. dv times u. So this is very, very simple. And then you can define that after this calculation here, you can see that the sensitivity of u times v to x, of course, u is function of x, v is function of x, and then you can say, aha, this is u plus sv over x. So this is another rule. This is rule number 8. And here, this is rule number 12. So usually there are tables with rules. This here on the slides belongs to tables. So here, two very important rules are given. Rule number 8 and rule number 12. So this is what I have shown here. Okay, so when we will use calculation of sensitivities, we will apply rules. Here is example. Probably you can recognize that this is the class 4. This is a bandpass filter. It has S here in the numerator, as you see. And then you can recognize what is omega p, what is qp, what is k in such a circuit. So if you want to see how is omega p variation because of G1 or G1, G2, which is 1 over R1, 1 over R2, C1, C2, or gain beta. So then you can calculate the variation of omega p. Also, you can calculate the variation of QP and the variation of K by the summation of all variations. Here, as you see, it has special form. Something which is called a under square root, and something which is called b is in the denominator without square root. So that's why we use this notation a and b, whatever it is. So then we can apply rules to calculate, and then we will see. We can calculate the sensitivity of let's say omega p square is 1 over R1, R2, C1, C2. Let's say it's like this. Then we can say S omega P over R1. This is something what we want to find. If we apply some rules, okay, then we can first start with S omega P square to R1. This can be 2 times S omega P over R1. What is S omega? Or we can write that S omega P to R1 is 1/2 S omega P square to R1. This is something what we will use. What is S omega P square to R1? This is S 1 over R1, R2, C1, C2 to R1. This is also S1 to R1 minus S R1, R2, C1, C2 to R1. This can be regarded as constant, which multiplies R1. So this here will be equal to, according to the rule, constant time epsilon is epsilon. So this is S to R1, and this is equal to 1. And here there is no R1 inside, so this is equal to 0. So our result is equal to -1. Okay, then if we know that this here is -1, then S omega P over R1 is -1/2. So you see how we start from this equation for omega P and calculate the sensitivity to R1. Okay? So this is applied here. I will not go into details. You can try to calculate all these things using our rules and tables. So this was very simple example. Now, the next question is how we can see our magnitude. What's going on? Let's say our magnitude looks like this. And if R1 changes 5%, then it can maybe look like this. So because of change R1, we are interested to see what is going on with our absolute T of j omega. So this was nominal. And because R1 has changed 5%, then you have the red one. Okay, this is changed. Now, to define this by equations, we have the following equations on the slide. So this is complex transfer function. And if we make some logarithm, then we have amplitude, response, and phi. And then if we calculate sensitivities of these responses and we apply this rule, then we can have two sensitivities, which are amplitude and phase sensitivities. So these equations are here. They are derived. Now, we can also rewrite them again. So we can say, if you can calculate st of s to the x, then delta alpha will be real part of st of j omega to x times delta x over x. So we know to calculate this because of using our rules, and then we just put s equal to j omega and look at the real part, multiply by this, and then you have delta alpha. You have delta alpha at some frequency. That means this is frequency dependent, because at some other frequency, it will be different. You will have delta alpha at omega 2. So this is omega 1, omega 2. So for different frequencies, you will have different delta alpha, and this is the equation. So delta x over x is delta x over x is delta R1 over R1. Okay. Okay, now when we see that we want to calculate delta omega p over omega p or delta qp over qp, then we have to make all these variations. Okay. Now just to repeat, if we have a transfer function like t of s, then you calculate transfer sensitivity, that's this. Then you put s equal to j omega, that's this, and then you obtain these two sensitivities. Okay. You see here that the real part is needed to obtain this here, delta alpha, or s to s of alpha to some element x. X can be R1, x can be omega p, qp, or whatever, and whatever. Okay, this is another graph which shows how these variations are looking like. They are functions of frequency. This is what I have just told you here. Another interesting property of function f is that it can be a so-called homogeneous function. And homogeneous mean if you multiply by some parameter lambda each of the variables xi, then you can put out lambda to the power of m, and then this power of m is the order of the homogeneity, and this is mathematical term. This will be useful in researching sensitivity, so that's why it's here on the slide. But we will not use it. Okay, here is something what is also important for a calculation of sensitivities. So homogeneity of omega p is 0. That means that all sensitivities to R's, if they are added, are equal to minus all sensitivities to capacitors if they are added. So this is the direct rule. And if you have in an integrated circuit so-called tracking components, then you will have some useful information. Now it comes another important thing, which is called multiple parameter sensitivity. What does it mean, multiple parameter sensitivity? Okay, we will show it very quickly. If you have, for example, let's say we go step here, we go to this example, and then we'll go back. If you have such a circuit which you recognize, which is called Sallen-Key low-pass filter, and then you can calculate something what is called sensitivity of T of S to QP. How it looks like. QP is from here, because A1 is equal to omega p over QP. So QP must look like this. R1, R2, C1, C2, R1, C1 plus C2 plus R2, C2 minus beta R1 C1. So this is QP. And we can calculate, for example, S of QP to R1. But before, we will start from here. And we will calculate ST of S over QP. What is ST of S over QP? So this is something like this. S of numerator, which is K omega P square, minus S of S square plus omega P over QPS plus omega P square to QP. And this comes from here. And then you immediately recognize this form, epsilon of x plus c. What is epsilon of x? It is this one here. And what is c? These two. Because these two don't have any connection with QP, only this guy in the middle has. And then you can apply our very, very famous rule. So S to, okay, this one here is 0, because there is no QP here. This is only constant regarding QP. So S to the S squared plus omega P over QP times S plus omega P squared to QP is equal to, let's say like this, omega P over QP times S squared plus omega P over QP times S plus omega P squared multiplied by S omega P over QP times S to QP. So that's it. And this here stays, and this here is equal to -1. So what is this? This will be -1 plus -1. This is equal to omega P over QP times S over S squared plus omega P over QP times S plus omega P squared. So this is ST of S to QP. That's very, very simple result. And this is calculated in a simple way. Of course, we have used this part here because this is 0 minus 1 times this minus here, and we have the solution. Now, we also say that S absolute T of J omega, not T of S, but absolute, to QP is equal to real part of ST of S to QP when S is equal to J omega. So you can try to calculate it, and you will find that this is equal to, I will write it here. This is equal to omega P over QP times omega square, omega P square minus omega square plus omega P over QP square. So this is this sensitivity. And now we want to find S QP to R1, for example, how much we will have here. If we apply all those rules, we can get as S to QP to R1 is equal to -1/2 plus QP R2 C2 over R1 C1. So now we have all equations that we need to obtain S absolute T of S, T of J omega to R1. This is equal to S absolute T of J omega to QP times S QP to R1, as you see. Then we also must check if there is something in the sensitivity of T of j omega to omega p times S omega p to R1 plus S T of j omega to K times Sk to R1. So this here is the sensitivity of our transfer function to, for example, R1. But we don't have only R1. We have R1, R2, C1, C2, and maybe we have gain beta. Here is gain beta. We know beta 1 plus, this is RF, this is RG, RF over RG. This is beta, so we can also calculate our sensitivity to the gain beta. So this is only one. We can use all of them. And then we can define something. If we add all these together and make square, we can define something what is called multiple parameter sensitivity, which is here. And we call it S2, and we call it Scheffler sensitivity. So the summation of the squares of these sensitivities to all parameters which are here, and we square it and then we add it. This is called Scheffler sensitivity. And then we find square root of it, and we suppose that all the elements are having 1% standard deviation, or let's say tolerance. Then we can calculate it in decibels. We use this equation, and this is multi-parametric measure for the sensitivity. This is all defined now, theoretical. Now I will show this all in examples, so you will see immediately. Okay. This example, so this whole circuit can be designed with different betas, different R's, and C. For example, we defined R2 over R1 as small r, C1 over C2 as small rho. What does it mean, R1? This means equal resistors. What does it mean, rho 1? This means equal capacitors. For all these cases, we can build the same transfer function. So all these cases will give us same transfer function, but where is the difference? Maybe something is better, maybe something is worse. Okay, here we see what is best. Best is number 3. Why? Because it has minimum sensitivity. And this is if you choose equal resistors and you choose C2 lower than C1. Then you will have the most accurate transfer function because it has lowest sensitivity. You can also look at Monte Carlo analysis. If you look at Monte Carlo analysis, you will again obtain that this is situation number 3. But what is the difference? Here you have 4 figures. Here you have everything on the 1 figure. That's all. Second example, if you try to build elliptic filter with 3 biquadratic blocks, which all has only 1 amplifier, so you need 3 amplifiers for the 6th order. And you here recognize the twin T, which is needed to obtain these zeros. These zeros are obtained using these 2 twin T. So we can make it. We can make it. Here is the characteristic. Okay. This is second example. Okay, this is first example. Cascade of biquads. We say in filter design, we always have two approaches. One is cascading of biquads. Another is simulation of ladder circuit. Now we'll see very soon what is the difference, because now we know sensitivity. Here is simulation of this ladder. So this ladder here can be simulated by many op-amps, for example, 7 op-amps, and then more resistors and capacitors. This is called DCR filter, but it's not so important here. You just notice that it has zeros here. Okay. And here finally we see the amplitude frequency by piece-wise of the both realizations. They all make the same magnitude, but where is the difference? If you make Monte Carlo analysis, or if you make Scheffler, it doesn't matter. We see that it's the same. You will see that this filter, although it has smaller number of biquads or op-amps, it has smaller number of op-amps. This will have lower sensitivity, a higher sensitivity, like this, where we need it. But LC simulation, which has bigger number of op-amps, it has much lower sensitivity. And in integrated circuits, number of op-amps is not a big deal. It's not a problem. We can have it as much as we want. But you notice here that this is the property of RLC filters. RLC filters, they have small sensitivity. Active RC filters, they have large sensitivity. So here we can say that this derivation of ladder network using active RC elements, you don't have any inductor here. You just have, instead of inductor, you have this guy, which is called frequency dependent negative resistor, but let's leave it for now. Just we want to say that this has low sensitivity. And this is very good because the amplifiers costs nothing in the integrated circuit. But here, this guy has maybe lower number of op-amps, but has much higher sensitivity, which you can see here in Monte Carlo. So in the PC Spice, you give 1% tolerance and you give 200 curves, and then you will have such a Monte Carlo analysis, which you can then analyze. So what we want to produce 1 million of filters in our factory. And then, of course, if we produce 1 million of filters, we will choose this one here because we will not have a lot of filters to throw in the garbage, into recycle. Okay, so this is the basic rule why we need low sensitivity filters, because they then can fit into our specifications and we can sell almost 1 million of them. So this is all for now for this lecture. Now we will have a 15 minutes pauses. After that, we will start with another lecture, which is called switch capacitor filters. It is also a very important lecture, and I will try to present it in 45 minutes. And after that, we will have questions. Thank you. Hello, we continue with our second presentation. It is lecture number 5, and we will talk about switch capacitor filters. Before we say something about switch capacitor filters, we have to repeat that there is big problem if you want to realize passive RLC filter in the integrated circuit technology. Why? If you look at the inductor, this is very big component. It has a wire, it has some metal, and how can you put it into the integrated circuit? It's impossible. So this was the reason why we turned into the realization of active RC filters, which can be realized. But also, if you look at the active RC filters, you have some problems. For example, sensitivity problem appeared all of the sudden, which was not by passive RLC filter, which we saw last presentation. So in integrated technology, it is also a problem to make large resistances. And capacitances larger than 100 picofarad cannot also be realized. But if you want to realize active RC filter with low frequency, then you need huge resistors or huge capacitors, and this is also big problem. And if you want to realize large inductance, it's impossible. Okay, so if you want to measure electroencephalogram, this is measuring voltages of the human body, of the brains, then you will obviously need very low frequencies, and this will be a problem. What are the advantages? Active RC filters are highly reduced. Capacitors are of very high quality. They are much higher quality than inductors. Inductors have usually they have a resistance of the wire, which capacitors don't have. Capacitors only have the resistance between the two plates, but which is very high. So the isolation is very good. So the capacitors are normally much better elements than inductors. Okay, now also to build active RC filters, we need amplifiers and transistors with high input impedances. Okay. So restrictions on the use of small capacitances requires the use of high resistances, and that's another problem. Then you will need larger area than for the capacitors. The tau, which is RC product, so F0 is omega 0 over 2 pi, and this is 1 over, so omega 0 is 1 over tau, is 1 over RC, so this is 2 pi RC. To have small F0, you need either high R or either high C. And there is also another problem. If you want to make resistor accurate of accurate value, absolute value on the chip, it's not possible. You will have 10 to 20% tolerances on the chip. So this is the same for the R and for the C. They both have the same tolerances. And what is then the tolerances of tau being RC? It is then 40%. So you will have big trouble to realize very accurate cutoff frequency, because you want 1 kilohertz and you will obtain 1 kilohertz and 400 hertz. So you will never know how much you will get it. So this is not the problem for the filters in realization of hybrid or in discrete component, because the R and C can be very, very accurate, and this is not the problem. But if you want to realize R and C in the integrated circuit, then it is really big problem. So this is the reason why it's not popular or realize active RC filters in integrated circuits. It's not good. It's not good idea. Okay, but now somebody found solution in the form of switch capacitor filters, and we will see what's happening. So before we continue to the slide 4, we will look at the example at the end. So here is the example 1. So this is the book which I will tell you later. This is the book where you can learn from all the theory about switch capacitor. But before we go to example, here the example says show dependence of the time constant of a switch capacitor integrator on the sampling frequency and realize a switch capacitor filter with integrated circuit MF10. What is MF10? You can buy it in somewhere. Now first we recognize our simplest RC integrator. So initial conditions are 0. Here you have virtual short-circuited input, so input current to the op-amp is 0 and voltage at the input of the op-amp is 0. So you can write these equations, and then you will have the very well-known transfer function of RC integrator. So the time constant is tau equal to RC. And then if you put step at the input, you will obtain this voltage here at the output. So this is the response of simple negative. You have minus here of simple negative integrator RC. Okay, now we replace the resistor in the input by this one capacitor and 2 switches. And these 2 switches are switched on and off by this clock. And then we can observe. For example, if S1 is switched on, S2 is switched off, then the capacitor C1 will go to the voltage E, which is the voltage of the U1. So this is the E. This is battery. Then when switch S1 is off and switch S2 is on, then this voltage goes to 0. Why? Because this here is the input of the op-amp. It is 0 voltage. We say that delta Q, which was in C1, the charge, flew into C1 and then out of C1 to the virtual ground. And this represents the flow of the charge in some time period, delta t. And then we can say that the flow of the charge, like charge pump, is indeed a current. And this current is equal to voltage times C1 times frequency of the clock, because this period t is one of the frequency. So you can say that this whole thing here, this behaves like the resistance. We can say what is the equivalent resistance? R, it is E over the current, and then if you put it here all inside, you can delete these 2 E's, and this is what you have as a value of the equivalent resistance. Then if we put this here and we have C2 and C1, then you will have the following very important equation for the time constant. Is the time constant so bad like here? No, not at all. Why? Because we have C2 over C1, which is the ratio of two capacitors. It's not 20%. It's probably 0.1%. That's very good. And then we also have F clock. This is also very accurate. Why? Because you can generate using clock using crystal oscillator, and you will have very accurate clock. And this is also very accurate. So altogether, this all of the sudden is very accurate. And this is not all. Besides it is accurate, it can be tuned. If you change this value here, you will change tau. Okay, so here is the output of such switch capacitor integrator. You see that the output is going like in stairs down, not any more continuous, but this is how it works. So it's, let's say, we call it not continuous time, but discrete time system. Here is the step. Step is also proportional to the ratio of C1 over C2. Okay. Now, if we want to make positive integrator, then we will add another two switches, which can be then switched on and off by some rules, and then you can have positive integrator. No, it will not go down like here. Now it will go up. So this is positive integrator. So just by changing some switches, you will be able to make it. Okay, now we remember the general purpose section, which has two integrators and one adder. Here are the positive switch capacitor integrators. This is chip MF10. You can look at the Google. And then if you want to derive the equations, they look like this. So this is not a big deal. This is amplifier at the beginning, at the input, and then you have to add all those signals together to obtain U2. After some calculation, you will have the transfer function, and you can read omega 0, Q, and K of the low pass transfer function. And then what you see here are tau 1 and tau 2, they deleted. So Q is not dependent of frequency of clock. Only omega 0 is dependent on the frequency of clock. Q is dependent of the component values, and K is dependent on the component values. The manufacturer of this chip, he made 50:1 the ratio of C2 and C1 and C4 and C3. So in his data sheets, he gives some more simple equations. So this is when you buy data sheets and chip, then this is the place where you start. So you don't know how he got these equations, but we have now just derived it. Okay. Now we will, using this one bicode, we will realize Chebyshev second order low pass filter with maximum 1 decibel and cutoff frequency of 10 kilohertz when the sampling frequency is 500 kilohertz. Here is some tables, which is not so important. You can look at any tables. So the tables will give us the Q, will give us omega 0. And here is the real and imaginary part. This is maximum frequency. But they are all normalized to omega h, which is the cutoff frequency. Then the cutoff frequency is equal to 1. And this is minus 3 dB. Okay, so you can read many things from the tables. So this is maximum. This is cutoff minus 3B and so on. Now you put it into design equation. You first try to obtain omega 0 and Q. And then you put it into design equations. You choose R4. And then you calculate R2 from omega 0, then you calculate Q, calculate R3 from Q, and then you calculate R1 to be equal to R4 to obtain the gain equal to 1. So you see that it's not very complicated to calculate the filter using only four resistors outside the chip MF10. So now this was example and everything we need to know for the beginning of our switch capacitor filters. Now we go back. So the same will be repeated here. So if you have a capacitor which has switch like this, or you can better use two MOSFET transistors with the clocks Phi1 and Phi2, then this in the middle will behave like resistors. So this is Q1, this is capacitor CR, which is loaded to voltage U1, and then he will have charge Q1. And then Q2 is this same capacitor with voltage U2. Delta Q is the amount of charge that capacitor transferred from A to B. Okay. Delta Q represents electric charge that moves from node A to B in the interval. This is the current. This is the equivalent resistor. This is all what we have seen already, but you can look at the slides by yourself, so it's not a problem. If the changes in the voltages U1 and U2 are fast enough, the maximum frequency in the spectrum of the signals must be much lower to cutoff to frequency of the clock. Then you can use simple replacement of resistors by one capacitor and two switches. If it is not, if the spectrum of the signal which is observed is very high, with very high frequency near to the clock frequency, then we must be careful that the spectrum of the signals must satisfy the sampling theorem of, let's remember, it is Shannon's theorem. And then in this case, we cannot just like that replace resistor by capacitor with two switches. In this case, we must solve all the switch capacitor circuitry using Z transformation, or the way how we know to solve discrete time systems. So it's not quite easy, but it's very accurate. Another good thing is, for example, if you want to realize large resistor, for example 10 megaohm, then you will be able to do it with only 1 picofarad, and for example with frequency of 100 kilohertz. So this is another advantage. You can realize very large resistances, not only that they are accurate, but the R, which is, let's say, equivalent, can be of very large amount, but with small area needed on the chip. So this is another advantage of the switch capacitor. Okay. The switches are implemented as MOS transistors. They must not overlap. So here, before one switch on, the guy before must be switched off. So here is the empty room. Okay. This is different way of. This is not so important, but I will just show you quickly. So you can connect these two switches in different way. So that's all. Approach to realization of filter circuits using switching capacitors instead of resistors solves some basic problems in realization of active RC filters in integrated technology. Frequency parameters defined by RC products are possibly to be tuned very precise by capacitance ratios and by the clock frequency. Resistors with high values can be realized on 100 times and more smaller chip area. So this is something what gained what was gained using this switch capacitor approach. Now, the second important thing is how to realize integrator with switch capacitor. If you replace R1 with this, then you from analog, which we have seen before, then you from analog integrator you obtain the digital one switch capacitor. Here are the equations. This is the transfer function of the analog, and this is when S equal to j omega is introduced of the analog integrator. Here is the clock signals. And now we can show that it is possible to derive the connection between voltages from input to output of the switch capacitor integrator. And this all here, what is explained, I will not go through this into detail because of we don't have so much time, but it's also complicated. And you can learn it by yourself from the books. I will show you where, if you want to derive the exact equation. I will just comment it. So this here, what is obtained is so-called equation of differences. It's not, it's something like differential equation in continuous time. Here in discrete time is equation of differences. And in continuous time, you apply Laplace transform. Here, instead of Laplace transform, you have to use Z transform. And if you apply Z transform to the delay, then you have multiplication by Z. So this is step n plus 1, this is step n. So they differ by one delay. So you recognize it. Okay. Here is no delay. Here is Z. This is transfer function into in Z domain. And if you want to look at the frequency characteristic of the Z domain, then you just have to introduce Z equal to e to the j omega t. And this is frequency characteristic. Now comes one very important and one very simple replacement for this function a to the j omega t by Taylor series. And we will see immediately if this omega t is also much smaller than 1, then it can be neglected. The higher potential. And in this case, all these can be neglected, and what is left is this. This is frequency characteristic of the normal integrator, which we had before. This can be obtained by replacing a resistor by one capacitor and two switches. So this is very simple case. When omega t, or let's say when frequency is much lower than the clock frequency, then the Shannon theorems is very, very much satisfied. But in this case, we can replace by simple every resistor in active RC filters we can replace by simple capacitor and two switches, and it will work because we see that this can be neglected. Okay. This is second version of these two, but we, as we said, we will not pay a lot of attention. This is derivation of the transfer function. Here is the transfer function. It differs from the first version, that the first version here has z to the -1, and this guy doesn't have z to the -1. Of course, the same is true when it is of low frequency. We can again have a very fast conclusion. By comparing the equations of differences for the first and second integrators, it is possible to conclude. The integrator for figure 4b, an instant value of an output voltage depends on the value of the input voltage from previous sampling period. And in the second case, an instant value of an output voltage depends on the value of the input voltage at the same moment. So this is the only difference. It's not so important to analyze it. Therefore, the first integrator introduces delay of output voltage of one sampling period, while the second integrator does not. Now, if you remember, we were talking about it. It's possible to build integrator which has two input signals that could be added. This guy here is needed for elliptic filters, and this is capacitor of integrator. Of course, if you add here one resistor, then you will have also losses. Each of these resistors must be realized using two switches and one capacitor. Here are the equations of this circuit. And of course, if this is a very low frequency of operation and with high frequency of clock, then you can have very simple equations. And we can say relatively non-demanding switch capacitor filters can be designed from active RC prototypes by simple replacement of resistors with their switching SC realizations when these frequencies of operations are like this. For more demanding switch capacitor filters, we must use accurate expressions from discrete domain. This is what we are going to use. Now, the next problem is parasitic capacitances. If you realize capacitors on the chip, there can be some problems with parasites. Here you see many parasites. Here, this is capacitor is here between these two, and it has one plate poly and second plate poly. Poly is leading current like metal, and oxide is insulator. So you see how this capacitor is made. Of course, here is one capacitor which is parasitic from this plate to the bulk. If you connect this plate here, then this guy will be dead. It doesn't make any trouble, but you can't do it with all of them. For example, this guy here exists. This guy is especially dangerous because this is reverse p-n junction, which has capacitance which is dependent on the voltage and on the many things, so it's not so good. Okay, CB is bottom, CT is C top, bottom plate, top plate, metal connection CM, and CJ is junction. It's nonlinear voltage dependent capacitance. All these parasitic capacitances can change values for 20%, which is very bad. Now, you see how these capacitors look like if you build integrator with them. You see, luckily, this is connected to the output voltage source of the amplifier. So this is output. So everything what is connected into parallel with low impedance of the voltage source, it will not exist anymore. So this guy does not exist. This guy also does not exist because it is here. This is here also 0 volts because it is virtual short circuit at the input of the amplifier. Here is also some voltage source of the generator. So this guy also does not exist. This guy does not exist because it is connected to the ground, you see. These guys too also don't exist because of the input to the voltage source, but what is left is altogether is here, this C to the CR, CP in C parallel. Okay? Now we see that capacitance CR plus C parallel will be transformed into equivalent resistance, and that the transfer function of the integrator has error. We have the wrong time constant, and it could be 20%. So It is also quite unpredictable because it's created by parasites. So this guy here make not this guy. This guy here make troubles. Okay. Now the people found solution to this problem. What is the solution to this problem? This is another problem, another way of making our capacitor to be connected to switches. We need 2 more switches. If you go here and up, then you can build it using these 2 pair of switches. If you have these 2 parasites, when these 2 switches are open, these 2 parasites will be short circuit and like they don't exist. Here is another version. If you change Phi1 and Phi2, then you have this form. You will see that this will be positive and negative resistor, and the parasites don't exist. So this was the solution. Luckily, when current which flows into CF could be realized using configuration with 2 switches. It's important to know that although parasites in figure 10 are loaded during the phase of V1 to U1 and then to U2 during the phase V2, they are harmlessly unloaded to the ground. So you can have positive and negative. Here you have integrators with switch capacitors without parasites, so it's very accurate. And then you can say, aha, just by changing these, then we can have negative or positive integrator, which is very good for realization. Okay. Here we need lossy integrators, lossless integrators, summing integrators with losses, and so on. So, for example, if you remember this R here, which is replaced by capacitor and 2 switches, is make the lossy inverting integrator. Another thing is very good for S switch capacitor integrators is that you can save some switches, because if you see if this Phi1 is on, then C1 and C2 are both connected to minus. If Phi2 is on, then C2 and C1 is connected to the ground. So we can save some switches. So here we can get rid of these 2 and connect this C2 here. And then we need some lower number of switches. This is also very characteristic for switch capacitor circuits. Here are possible different kind of transfer functions. This is, let's say, general switch capacitor building block. It has everything. It has losses. It has two inputs. One is positive, another is negative. You see, just by changing this phi. Here is the C free, which goes directly to output without integration. This is needed for elliptic filters and so on. So this basic building block can do everything, and it can be realized using switch capacitor. Okay. This is his equivalent resistance. This is output voltage, and the phase difference in switching on the left is to make this minus of the left plate of C2 on the previous slide, which I have told you already. Okay. Once again, we must repeat that all the transfer functions till now we have derived using the following assumption, where Fc is the clock frequency and F is the highest frequency in the signal spectrum. And under this condition, all circuits are almost time continuous. And as we have told till now, the case of less demanding projecting can be done in simplified way. We can start from active RC filters and simply replace resistors by switch capacitor variant. So then it's very simple design. Otherwise, we must derive exact equations. Here is example how we can derive exact equations. So as the frequency of the signal is growing compared to the clock frequency, it is noted the growth of deviation of the filter characteristic from these specified. That means more careful analysis is required. We will conduct analysis by writing difference equations in the same way as we do for the time discrete systems. And what is the most important, obtained analysis will be exact, so we don't make any approximation. So here begins the derivation of our time discrete equations. Let's suppose that sampled signal V1 of n changes its value instantly only in a small fraction of time after the period of clock t, for example, during the phase V1. And then the input V1 of n is constant through the next phase, so we can write this. This will be used in derivation of equation. This is the equation. This is the current from this here picture. And if we integrate it from period n to n minus 1/2, because the time is normalized to big T, we have T over T, then you have n minus 1/2, you have n, and so on because of this. You also can conclude that these C1V1 and C2V2, which are the charges, are 0. Then you can write this equation. This is with this first figure. At n minus 1 is the second figure, where the switches are in different position. So here we can also delete C2 without problem. And then we can derive the equations which are valid for with or without C2. This is the operation of inverting loss integrator during phase 1 and phase 2. So to analyze how they work, it's always the best to draw the circuits for the two phases, phi1 and phi2 separately. Okay. At the end, you have this difference equation. So this is the most important. If you can derive it at home, then it will be good. You can look at the books. I will show you where, and then you probably can come to this. This is called difference equation, and this difference equation is solved using the Z transform. So this is from discrete time system analysis. Okay. Now you can also analyze another guy with losses and with which is non-inverting integrator. Then you will have a little bit different equation, but all very similar. So this is another figure. So here are the switches differently switched on and off, and looking at these two pictures for phase phi1 and phase phi2, you can derive the second equation. Now, if you want to write equation for the general block in figure 13, you obtain this. This is the general equation for the block in figure 13. This one. So this one is described by the difference equation, which has everything, has summation, minus, plus, it has this losses, it has direct signal integration, without integration, and so on. So this guy here on the figure 13, it has the following, this one here. This is basic building block. It has its own equation. Okay? We can conclude in the analysis of switch capacitor filters and their integrators, we need to write difference equations and then use Z transformation. It is possible to full integrate the filters on the chip. This design saves silicon. There is no need for the on-chip adjustment. But now, what is the difference between the continuous time? Here we need circuits for switching. We need in the beginning anti-aliasing filter. What is anti-aliasing filter? We need to block all the frequencies that are too high, that aliasing will not occur. These are the frequency higher than the 1/2 of the clock frequency. So this is Nyquist theorem. You know it probably. Then you need sample and hold circuit, or you need either sample and hold, or you need just simple sampling circuit. So this all comes before our switch capacitor filter. After switch capacitor filter, you need circuitry for signal reconstruction. This will be simple low-pass filter. But if you use sample and hold, then you will need some equalizer, and so on. This all requires additional silicon area and creates additional noise. This required sampling, together with technological limitations, narrows the frequency range of signals. So these switch capacitor filters are not used everywhere. They are used in, let's say, low frequency applications, and it's, although it has many advantages, it's quite complicated. So it's not so simple to use them. Okay. Now we can also say if you have digital signals, then you don't need this circuitry. Then it's simple. So all this you can find in the book, which is quite old book, but because this is a basic material, so it's forever usable. Now I will try to look at our book, which we know already, if it has something about switch capacitor filters. It has about sensitivity. So if you want to learn sensitivity, this is chapter 12. And chapter 17 is switch capacitor filter. So you can learn it from the book, which you already have. So switch capacitor is the last, which you have on your materials. Here another book, which you also have. It also must have switch capacitor filters, so you can learn it from many books. And here you also in this, so in both books you have everything what you need. You also have, let's say, sensitivity theory. So here are the slides which I have used. Some of them you probably recognize them. So these are the tables and so on. So our examples. Here you have more examples, which I didn't want to show you because it will be too much. But if you want to study it one day, you can read it from this book. Okay, so you have everything in the books. You have everything about switch capacitors. You have everything about sensitivity, which we were learning today. I just wanted very quickly to show you how this is, let's say, complicated or simple or whatever, but I think it's not quite simple, but it's very useful to know something about this. Now I will tell you goodbye and I will stop the recording. Bye-bye.
Wait.